Hello friends, so welcome to lecture series on essential mathematics for machine learning. In the last lecture, we have seen the basic concepts of SVM. We have seen that if you are having two class of data points and if we are able to find a hyperplane which can classify the two classes, then they are linearly separable, otherwise they are not linearly separable, means they will be non-linearly separable. Also we have seen one result, that means if we are having a two sets and if their convex cells are disjoint, then that means they are linearly separable. So this condition is if and only if. So that means if the convex cells are not disjoint, they will not be linearly separable. So now the question arises that is there any mathematical formulation of such type of problems, that seeing a mathematical result we can analyze whether a given set of data points are linearly separable or not. So the answer is yes, and that is error minimizing LPP. So what do we mean by, and how we can formulate error minimizing LPP? By seeing that problem we can see that whether the given class of two class of data point is linearly separable or not. So how can we formulate? So this we have already seen that by suitable scaling these two inequalities can be converted into these two inequalities. Okay. We need greater than equal to type or less than equal to type to deal with the LPP, linear programming problems. How can we solve the problem? Let us suppose A plus is equal to maximum of A or 0. If A is positive, it will be A, otherwise if A is negative, it will be 0. Now if x is in Rn, what do you mean by x plus? X plus, in that case x plus means plus of 1, I mean this x, see, if x is in Rn, so that means x is equal to x1, x2 up to xn, such that each xi belongs to R for Ri. Okay. Now if I am telling x plus, so that means x1 plus, x2 plus and xn plus, and plus means if I am taking x1 plus, that means maximum of x1 or 0. Okay. Now here I am taking L1 norm. What do you mean by L1 norm of x? L1 norm means summation of mod of xi. Okay. X is in Rn, so this L1 norm here means I from 1 to n mod of xi. Okay. Now consider the following optimization problem. See what optimization problem I am taking. See here this A plus W I am taking in the right hand side. So this A plus W, when it go right hand side, then it will be minus A plus W plus EB plus E less than equal to 0. And similarly here I am bringing these two terms in the left hand side. So it is A minus W minus EB plus E less than equal to 0. So here we are having that term. So it is, there are M1 points here. Okay. So this M1 points plus norm 1, and here also M2 points and norm 1. Okay. So plus means what? Plus means maximum of, if I am taking A plus, that means maximum of A and 0. Now here each term is less than equal to 0, it is less than equal to 0, it is less than equal to 0 if this value, entire value comes out to be 0, then this means they are linearly separable. Why? Why it is so? See, there are two terms here and both the terms are non-negative because norm 1 is there. Norm 1 means sum of mod values, sum of M1 values here, sum of M2 values here, and if this comes out to be 0, that means each term is equal to 0, and if this is 0 and this plus means plus means maximum of a and 0. So, if it is 0, that means none of the term is positive, all are 0, then only it will be 0. Similarly, here also all the term will be 0. Okay. So, if that means this inequality is true, and here also this inequality is true. So, if this inequality is true and this inequality is true, that means we are able to find a hyperplane satisfying these two inequalities, and that means the classes are linearly separable. Okay. And if this value is not 0, if this value is not 0, that means there will exist at least one point for which this inequality is not holding, does not satisfy at least one. So, that means the classes are not linearly separable. Okay. So, here the same thing is there, that if a plus and a minus are linearly separable, then the error, we are calling this as error, then the error is 0, and hence the optimal value of p is 0. The converse of the statement is also true. If it is 0, then the error will be 0. Hence, this optimization model helps in predicting whether or not the sets a plus and a minus are linearly separable. Now, the question is that it is not a LPP, it is a non-linear problem. How can we model it in a LPP or a simplified way, so that we can predict, we can solve it, and we can find whether a given LPP is, whether a given problem is linearly separable or not. So, to simplify this, so let us understand it here. So, what is problem P? Problem P is minimum of norm of minus a plus w plus E b minus E norm plus norm 1 plus, it is 1 by m 1 times, and here 1 by m 2 times norm of, here norm of minus and plus, yeah, okay. So, it is also plus, and it is a minus w minus E b plus E norm plus norm 1. Okay. So, this is the problem, and if this error comes out to be 0, that means the given data points are linearly separable. Okay. So, now how can we convert this? So, let to minus a plus w plus E b plus E plus. Okay. So, this means it is maximum of minus a plus w plus E b plus E or 0. So, if it is maximum of these two, this implies first of all, this implies y is greater than or equal to 0 and y is greater than or equal to minus a plus w plus E b plus E. Okay. Similarly, let z equal to a minus w minus E b plus E plus. So, that further means maximum of a minus w minus E b my plus E or 0. So, this implies z is greater than or equal to 0 and z is greater than or equal to a minus w minus E b plus E. So, this point and this point. Now, let us put y and z here in P. So, P becomes, see, if you put y here, so now it is nothing but norm of y, okay. And since y cannot be negative, because y is either 0 or positive from this. So, since y cannot be negative, so mod of y will be itself, and we are summing it, because by the L1 norm this is nothing but sum of see, this is nothing but sum of I from 1 to m1 times mod of yi times 1 by m1 plus 1 by m2 summation j from 1 to m2 mod of zj, subject to these conditions, these 4 conditions. Now, since yi cannot be negative, because it is maximum of this and this, either it is positive or 0. Similarly, z is either positive or 0. So, it cannot be negative. So, mod will be itself. So, this will be equal to 1 by m 1 summation I from 1 to m 1 y I plus 1 by m 2 summation j from 1 to m 2 points z j, and this can be further written as m 1. So, it is what? It is y 1 plus y 2 plus y 3 up to m 1 times y m 1. It is z 1 plus z 2 plus z 3 up to z m 2. So, this can be written as y transpose E. E is vector of ones, y 1 plus y 2 plus y 3 up to y m 1, and this is 1 by m 2 times z transpose E, z 1 plus z 2 plus z 3 up to z m 2. So, this will be the objective function subject to these constraints. Now, the problem will be what? The problem can be recast into E transpose y or y transpose E, both are same, upon m 1 plus E transpose z upon m 2 subject to these conditions where w and b are unrestricted in sign. So, this is a simple linear programming problem, and we can solve it very easily by using any LPP solver. If this value of the objective function comes out to be 0, that means the problem is, the classification problem is linearly separable. Okay. So, let us discuss an example based on this. Okay. So, example is, this is an AND problem where A plus having a 1 data point and A minus having a 3 data points. So, what is A plus and what is A minus? A plus contain only 1 data point 1 1, and A minus contain 3 data points 0 0 1 0 0 1. These are 3 data points in. So, if you see by geometry, then A minus is 0 0 1 0 and 0 1, these are 3 points, and A plus having a 1 point, only 1 point 1 1. So, of course, the convex hull of these 3 are only this, and the convex hull of this point is itself. So, they are linearly separable. But let us verify this result by formulating error minimizing LPP. So, how can you formulate the error minimizing LPP? So, let us see how many points here, only 1. So, there will be only one y, say y 1. How many points here? 3 points. So, there will be 3 variables here, z 1, z 2, z 3. So, what will be the objective function? The LPP will be, objective function will be it is y 1 plus 1 by 3 times z 1 plus z 2 plus z 3. It is 1 by m 1, m 1 is 1 because there is only 1 point, 1 by m 2, m 2 are there are 3 points 1 by m 2. So, minimum of this subject to what are the conditions. So, let us see the first condition. The first condition is A transpose W minus E B plus y greater than equal to E, okay. A plus W. Now, A plus W, A plus means 1 1, okay. That means A plus W, that means W 1 plus W 2. W is not a single W, it is in R 2. So, W 1 plus W 2, then it is minus E B minus B plus y 1 greater than equal to 1. Next is minus A minus W. So, minus A minus W means minus. Now, when you multiply this first point with W 1 W 2, it will be 0, okay. So, that will not come. So, that will be plus E B plus Z, plus E B, that means B plus Z 1 greater than equal to 1, okay. Next, third point is again minus of W 1 plus B plus Z 2 greater than equal to 1, minus of W 2 plus B plus Z 2 Z 3 greater than equal to 1, y and Z 1 Z 2 Z 3 are greater than equal to 0, and B W 1 W 2 are unrestricted. So, this will be the error minimizing LPP which we have formulated here, the same we have formulated here also, okay. Now, if you solve this LPP by any LPP solver, So, what we obtain? We obtain that W1 equal to 2, W2 equal to 2, B equal to 3 and Y1, Z1, Z2, Z3 all are 0. So, that means the value of the objective function comes out to be 0 because all are 0, and since objective function comes out to be 0, that means problem is linearly separable. And what is the linear classifier? Linear classifier will be W1 x1 plus W2 x2 equal to B. W1 is 2, W2 is 2 and B is 3. So, that means x1 plus x2 equal to 1.5 is a classifier. Okay. So, similarly, if we are having XOR problem, okay. So, what is XOR problem? XOR problem is A plus are 1 0 0 1 and A minus is 0 0 1 1. Okay. So, if you see here 1 0 is something here, 0 1 is something here, 0 0 is something here and 1 1 is something here. So, the convex hull of these 2 points is this line and the convex hull of these 2 points is this line. So, they are not disjoint. So, that means they are not linearly separable. So, the same thing we can also verify it by formulating error minimizing LPP in the same way. Okay. So, if we formulate a error minimizing LPP, so we will get this LPP and by solving this we can find the optimal solution as W1 equal to W2 plus equal to B equal to 0 and Y1, Y2, Z1, Z2 all are 1. So, that means the value of the objective functions comes out to be 2. So, since the value of Z is not 0, that means the problem is not linearly separable. Okay. In this way we can analyze whether a given whether a binary classification problem which we are having, by formulating a simple LPP we can find out whether a given classification problem is linearly separable or not. Okay. Now, we have some basic definitions. What are definitions? The first definition is margin. What do you mean by margin? For a plane W transpose x equal to B, the distance between these two bounding planes, W transpose x equal to B minus 1 and W transpose x equal to B plus 1 is called the margin, the distance between these two bounding planes. Now, you are having this type of structure, you are having plus 1 class, you are having minus 1 class. Suppose this is W transpose x equal to B minus 1 and this is W transpose x equal to B plus 1. This is on the point W transpose x equal to B plus 1 and this is some plane which is W transpose x equal to B. So, distance between these two bounding planes is called margin. So, what is the distance? What is the distance between these two planes? So, the distance is clearly between these two planes is 2 upon norm of W, the distance between these two hyperplanes. Okay. You find out distance from origin to this plane, and the difference between the two is nothing but 2 upon norm of W, that will be the distance between these two hyperplanes. Next is canonical separating hyperplanes. Let A plus and A minus be linearly separable, we are assuming. Then a separating hyperplane W transpose x equal to B is called canonical separating hyperplane if it satisfies this and this inequality. Okay. So, this plane will be called canonical hyperplane if we are able if this and this inequality holds. Now, optimal separating hyperplane. Now, in this if you see these are linearly separable, but there are infinite number of so many hyperplane which can be found which can separate these two classes. But what will be an optimal separating hyperplane? So, how do you find optimal separating hyperplane? So, suppose this is an canonical separating hyperplane. Okay. Then the separating hyperplane, this is called optimal hyperplane if the margin between these the bounding plane is maximum. And that means if this distance maximum, which is the distance between the two bounding plane, then we say that this plane is called optimal separating hyperplane. Now, what is the dead zone? So, this here this region is called dead zone. So, dead zone basically means all those region where W transpose x is less than B plus 1 and greater than B minus 1, this region where there is no point from A plus or A minus, that region is called dead zone. So, now what will be our aim, next aim? We have seen that whether two classes are linearly separable or not, that we have seen mathematically also or geometrically also. But if we are interested to know that what will is the optimal separating hyperplane, that means we have to maximize this distance, or this to maximize, or we have to minimize this distance. Now, the question is, if we are minimizing this distance, then how can we solve this? How we can find out the optimal separating hyperplane? Okay. So, that thing, so this I have explained by the geometry. So, that thing we will explain in the next class, that if we are having a, if we are interested to find out an optimal separating hyperplane, given that it is a linearly separable, then how can we formulate an optimization model for this. So, thank you very much.